So far, we've been exploring the consequences of all observers having the same speed of light. We've seen that this has forced us to rethink what we mean by space and time, that different observers have different experiences of it. And we've also seen that we've had to modify the Galilean transformation to the Lorentz transformation in order to be consistent with this. This turns out not to be the end of the road. Normally, when theoreticians modify things, what winds up happening is you get sort of a game of whack-a-mole happening, where you modify one thing, discover that something else is broken, you modify something else, discover that something else breaks, and then eventually just too many things break and you give up. But every so often, as you go along, you discover that after you've made enough modifications, everything works again. And that's what happened with Einstein as he was developing relativity. So here's the next problem that we have. Let's go back to a problem we've done in mechanics. You have two masses, massless spring connecting them. We just go ahead and let them fly. So this is what our observer S sees. So our observer S would say that the total momentum before in the x direction is 0. And afterwards it would also have to be 0. And sure enough, one's going to be flying off, going ux to the right, the other is minus ux to the left. So you'd say, okay, px is m times minus ux plus m ux, also equal to 0. Momentum is conserved. We had the same before and after. But now let's go boost over to S prime's frame. S prime is in the frame where they're going to see V equal to this final ux. So they're seeing this whole thing sliding over in, well, we'll say ux prime, just to be very careful. So we'll be seeing the whole thing sliding over, and then after they decouple, this one will be at rest, and this one will be going at a speed, so we'll say ux initial. This will be going at a speed of u prime is equal to, well, we can go ahead and do the boost. It'll be u, which is equal to v, plus v, so that's 2v over 1 plus uv, so that's going to be v squared c squared. Okay, so before, the x component momentum was minus 2mv, and after, it's minus 2mv, all right, over 1 plus v squared over c squared. This is a problem. These are not equal, and they should be. So what Einstein showed was that you had to redefine momentum. And it's beyond the scope of this course to prove that it works, but I can go ahead and say what the redefined momentum had to be. The correct expression for momentum turns out to be that P is equal to mu over the square root of 1 minus u squared over c squared. So this is our new definition of momentum. We get the classical definition when things are going slow. U over c will be basically 0. You'll be left with m times u. That's what we've always had before. Now, confusingly, physicists call this gamma mu. This 1 over 1 minus u squared over c squared. This is not the same gamma that we've been doing before, which depended on v. However, it's usually clear from context which one you mean, and there's only a couple of fairly pathological calculations where you have both kinds of gammas at the same time. And so when you have one of those situations, what people usually do is write gamma sub u and gamma sub v to keep the two straight. But anyway, you can show that, yes, momentum conservation holds in all reference frames with this choice. Now, what is this going to mean for the work energy theorem? So remember, the work energy theorem says if I take some object and I start pushing it from rest, its kinetic energy will be equal to the work that I did on it. So this will be the integral from u equals 0 up to our final speed u of f ds, assuming we're just doing this all in one dimension. Now, remember back from physics 243, it's usually the case that you can say F equals ma, but when things are going fast, you actually have to use the correct statement, which is that the force is equal to dp dt. Okay, so this will give us an integral of, well, this will be d dt of gamma m u with respect to s, and you can integrate it from 0 to u. Yes, I know we need to be getting this rearranged to integrate it in terms of u. We can rewrite this as integral 0 to u d of gamma m u ds dt. That helps a little bit because then that makes this a u right here. Then we can observe that the formal differential of gamma mu would be mu d gamma plus gamma m du. When you go ahead and take the derivatives of all that, you will end up getting that this is m times 1 minus u squared over c squared to the negative 3/2 du. And then you can take that, substitute into there. So you'll be left with our kinetic energy being the integral from 0 to u du of mu 1 minus u squared over c squared to the negative 3/2 power. You go ahead and you evaluate that, you get the kinetic energy is gamma minus 1 mc squared. Now, when you look at that, that looks nothing like the classical expressions that we've been used to. But let's just play with that for a moment. So checking the correspondence principle, let's say that u is much less than c. This gamma minus 1 expression, k, is 1 over the square root of 1 minus u squared over c squared minus 1 mc squared. If I go ahead and start Taylor expanding this, I will get that this is equal to 1 plus a half u squared over c squared plus higher terms. Then we're left with this minus 1 from before, mc squared. All right. The 1's cancel. So I'm left with 1/2 u squared plus c squared. Since we're saying u is really small compared to c, this term is basic. The only reason we're keeping it is because it's the first thing that isn't 0. these things are going to be higher powers of u and c, so we're going to say that those are effectively 0. That lets me cancel the c squareds here, and I am left in the limit of things going slow, 1/2 mu squared. Yay. So it actually does check out classically. But now let's go and look at what happens as things go towards the speed of light. So we'll say we'll let u approach the speed of light. Well, as u approaches the speed of light, gamma will be approaching infinity. So that means that k, since that's gamma minus 1 mc squared, that will also approach infinity. So if you have a massive object, if you want to get it to the speed of light, you're going to have to do an infinite amount of work. And since there isn't an infinite amount of energy available in the universe to do that, what we can conclude is that the speed limit is 3 times 10 to the 8 meters per second. Nothing can go faster than this. So that's where, now if you're massless, you can only go at that speed, and if you're massive, you have to go at less than that speed. Okay. You've probably already seen this mc squared thing playing out. You're going, that's looking an awful lot like E equals mc squared. Where's the rest of that going to come from? Well, where the rest of that comes from, and again, I'm glossing over some stuff here, but just like we saw that in order to have position time obey the Lorentz transformation, right? Momentum obeys the Galilean transformation, so we'd like it to obey the Lorentz transformation too. So for momentum to obey the Lorentz transformation, we need a time-like part for the momentum to stick into the Lorentz transformation relations for it. The time-like part of momentum turns out to be equal to, turns out to be E over C. And we have to have a very specific definition of E. And that is that it's gamma mc squared. Well, that's interesting. So Einstein showed that yes, we can get the Lorentz transformation to work if the total mechanical energy of the particle is gamma mc squared, but we've only accounted for the kinetic energy of it so far. So we have that E is equal to gamma mc squared. That's got to be equal to the kinetic energy plus, I'll call it E naught, which that would be gamma minus 1 mc squared plus our E naught. To get the books to balance, what we're saying is, okay, this is the energy associated with motion. That's gamma minus 1 mc squared. We're off by this factor of E naught equal to mc squared. How do we interpret that? We just say that this is the particle, the energy associated with the particle when it is at rest. We call that the rest energy. The best way to interpret that I've ever heard was one of my professors in grad school who put it, that's how hard God had to work to make the particle. And we can indeed actually do that. Give me a moment or two and we'll show that yes, you can actually make particles and that the energy associated with making those particles is indeed their rest mass times the square of the speed of light. But since we've now shown that momentum with this E over C bit being the time-like component is also respects the Lorentz transformation, that means there is another relativistic invariant, and it is this rest energy. You can show that the square of this rest energy is equal to the total mechanical energy minus PC squared, where P is the relativistic momentum of the object. So this might be a fast way, if you have the momentum or the energy already, to solve for the other thing. Okay. So let's do an example of how we can make or destroy matter. Now, I know, you're saying, wait a minute, my chemistry professor told me matter can neither be created nor destroyed. That's not quite right. It turns out that when you have a chemical reaction, if it's exothermic, a tiny little bit of energy that got released from the bonds, the chemical bonds holding the molecules together, because you're now in a lower chemical potential energy state, if you were to weigh those chemicals super carefully, if it's an exothermic reaction, you would see that the products weigh just barely less than the reactants. However, for chemical processes, it's basically impossible to do this measurement. Nuclear processes, however, the potential energies involved in the strong nuclear force are much larger, and these differences are noticeable. So to that effect, let's go and take a look at what happens in the core of the sun. Oops. It's a process known as the Proton-Proton Chain. Now there are several different paths it can take, but I'll just go through the main path that happens in the sun. Every so often, two hydrogen atoms, because of the very high pressure and high temperatures in the core of the sun, every so often you'll get so lucky that two protons happen to fly straight enough at each other, going fast enough that they get past the desire of the electric force to repel them, and instead the strong nuclear force seeks to attract them against that. For that to happen, they have to get on the order of a femtometer apart. So they have to get super close. It's rare, but there are so many hydrogen atoms in the sun that even incredibly rare things happen fairly routinely. So what happens is one of our hydrogen atoms, so just a proton, will collide in with another proton, and it will make an isotope of hydrogen called deuterium. So this is one proton plus one neutron held together by the strong nuclear force. Now, in order for the charge books to balance, the weak nuclear force kicks in and you eject a positron, which is a positively charged electron, not the same thing as a proton, plus a particle called an electron neutrino. An electron neutrino. The main thing about these neutrinos is their mass is almost, but not quite zero. We have experimentally demonstrated it's definitely not zero. However, the best we've ever been able to do so far is just to give very low upper bounds as to what their mass might actually be. And these particles basically don't interact with anything. They shoot right out from the core of the sun. 8 minutes later, they shoot right through us and pretty much undeflected. Only very rarely will one of them happen to interact with something on the Earth. But we have built the absolutely enormous detectors required to catch these incredibly rare interactions to see that, yes, indeed, these neutrinos are flying out from the core of the sun. Okay, so we now have what's called a deuteron, one proton plus one neutron bound together by the strong nuclear force. In the second step, another proton will come in. Oops, let's do better. Another proton will come in and combine with one of these deuterons. Now, we wind up making helium-3, but the way the protons come in together, it turns out that one of the protons will be in an excited, strong nuclear energy state. So we put a little star here to indicate that it's excited. That almost immediately transitions back down, though, to become a ground state helium-3 atom plus a high energy photon. Okay, then in the last step of this process, two of these helium-3s get together. And they will combine to make the more typical helium-4 nucleus. Now, in this case here, the electric force does win out, and two of the protons go flying out. Now, for all these things, for all the products that go flying out, with the exception of the neutrinos that basically don't interact with anything to speak of, everything else will pretty much rattle around in the interior of the sun. The kinetic energy that's carried off from this will go to produce heat in the sun. That heat will work its way up to the surface, taking a very long time to do it. And then the photosphere of the sun will radiate that heat off as electromagnetic radiation. Now, electromagnetic radiation will then take an 8-minute trip over to where we're at. Some of that will land on some wheat or something, and hey presto, you have yourself a Pop-Tart. Now, how much energy are we getting from this? Let's just focus on this process right here. This first one, hydrogen plus hydrogen yields hydrogen-2 plus a positron plus an electron neutrino. So let's calculate the change in the rest energy. So we'll go ahead and take the products. We have a helium-2 nucleus, and you have to, when you're doing these calculations, you have to do them to a ridiculous number of significant figures. 2.014102 atomic mass units. Oops, sorry. Let me back up just a second before we do that. So this will be the rest energy of the hydrogen-2 nucleus times c squared, so mc squared, plus the rest energy of the positron, mc squared, plus, well, I'll put it in there, the mass of the neutrino, c squared, but I'm just going to basically say this is roughly 0. It's basically not even a rounding error. We just know that it's not 0. Okay, now I've looked up the atomic masses of all these things. The atomic mass of hydrogen-2 specifically is 2.014102 atomic mass units. And we will convert that to MeV per c squared, which is 931.49 94013 million electron volts per c squared, and then we're timesing by c squared, plus the mass of the electron in MeVs is 0.511 MeV per c squared, and like I said, the neutrino basically doesn't count. Now from all that, I have to subtract the reactants, so it'll be 2 times the mass of a hydrogen 1 c squared. So subtracting that, so minus 2, the atomic mass of hydrogen 1 is 1.007825 atomic mass units. Again, we'll be doing the same conversion, 931.494013 MeV per c squared. Alrighty. So if we cancel that out, this c squared and that c squared cancel. Oops, I forgot to carry a c squared here. This c squared and that c squared cancel. This c squared and that c squared cancel. Also forgot to say per u here. The u's cancel. And we are left with minus 0.931 million electron volts. So nearly 1 million electron volts. Remember, an electron volt is about 1.6 times 10 to the negative 19 joules of energy. So this is on the order of 1.5-ish times 10 to the negative 10 joules. Not an awful lot by human standards, but for an atom that's an awful lot. There are an awful lot of these processes occurring every second, producing an enormous amount of heat in the sun. But what this does also mean is if you just plain add up all the masses of these things, the mass of the reactants is indeed, the mass of the products is indeed just a little bit less than the mass of the reactants. And that very slight change in mass as this process goes through is the source of the energy that drives the sun. That in turn drives photosynthesis. That in turn gives us our Pop-Tarts for breakfast. Okay, where I would like to finish up relativity is to revisit that same problem we had at the beginning. So remember, at the beginning, I asked you to think about an electron gun. So there's my electron gun. There's the filament. We're having electrons coming off of it. It's between a couple of plates. This plate is negative. This plate with a little hole in it is positive. The voltage difference I said was 1.022 times 10 to the 6 volts. So some of these electrons will go flying out through the hole, and I wanted to calculate what was the final speed of the electron after we accelerated through that. So now we'll have to do it relativistically. So when we do the energy conservation, you'll have to use the new kinetic energy term, and U gets buried in that gamma. So go ahead, give this a try, pause the video, and then we'll loop back. Alrighty, so we start the same way we started before. We can say that the kinetic energy that we have at the end had to be equal to the potential energy we had at the beginning. So this will be gamma minus 1 mc squared. And this has to equal our E delta V. Okay. So let's go. So here, let's just start by solving for gamma. And then once we solve for gamma, we can rework that to solve for beta. So all right, we can divide both sides by mc squared, add 1 to both sides. We get that gamma is 1 plus E delta V over mc squared. All right, so this is E times 1.022 times 10 to the 6 volts. And this is 0.511 times 10 to the 6 EV per C squared. Alrighty, times C squared. Alright. So once again, we can cancel our C squareds. We didn't substitute in for the E because you had that E in the electron volt unit, just so you could cancel it. Volts cancel. 10 to the 6's cancel. That cancels against that, leaving a 2. And oops, I dropped my 1 plus. So 1 plus 2 is 3. All right, so we have that gamma is 3. All right, now remember gamma is 1 over the square root of 1 minus beta squared. We know that's got to be 3. So 1 over 1 minus beta squared would have to be 9. All right, let's cross multiply. 1 minus beta squared would be a 9th. So beta squared is 1 minus, oops, this 1 minus 1/9 is 8/9. So beta would be the square root of 8/9, which is 2 root 2 over 3. Our final speed is beta c. So this would be 2 root 2 over 3c. You punch 2 root 2 over 3 into your calculator, and you'll get 0.943c, which does indeed match experiment. So have fun, and I will catch you in the next one.